Let's build some Taylor polynomials and a Taylor series ultimately for a given function around a given point. It actually, for the understanding of this, the function and the point that we're working with is sort of irrelevant, but we happen to be working with the function 1 over x, and we're going to establish Taylor polynomials and a Taylor series for that function around x equals 1. Just a reminder of what that means graphically. Right here, we're looking at a graph of 1 over x, the black curve right there. Everybody knows what 1 over x looks like. And what we're doing is we're building a sequence of polynomials of increasing order that are anchored at the same point as 1 over x, at x equals 1, and that become better and better at approximating 1 over x the more terms we add on. So the red curve right here, just for instance, could be, say, the fourth order Taylor polynomial, that is, the Taylor polynomial going out to an x to the fourth term, which is designed to mimic 1 over x in a region centered on x equals 1. But since it's a Taylor polynomial, it only has 3 or 4 terms to it, then after a short distance away from 1, it kind of loses its mojo and it ends up diverging from the function 1 over x. But if we go put more terms on it, then the range of agreement may get wider and wider. And ultimately, a Taylor series is an expression with an infinite number of terms that does the best job that the sequence of increasingly complex Taylor polynomials could do in order to mimic the given function. Now, that's the conceptual overview of these things. Here's the formula, right? You see this and it's like, oh, what the heck is that? So don't get overwhelmed. I know there's a summation on it, but that's okay. Just take the summation away for a second. Recognize that this is a polynomial. The numerator of this fraction represents the nth derivative of your given function evaluated at the anchor point, x0, and so that's just going to be a number. N factorial for any given n is just a number. The only variable we actually have here is x. X is the variable. Here's the anchor point. It also appears there. And so this says we have an x minus some number to the nth, so squared, cubed, fourth. And the higher that gets, the higher order polynomial we have. Since a polynomial is a sum of a bunch of different terms, right? Well, that's what the summation is doing. And so if we take this summation from n equals 0 to, say, 5, that's the fifth order Taylor polynomial, 0 to 10 becomes the 10th order polynomial, and say the highest power of x we would see is 10, and we'd probably expect to see an x to the 9th and 8th and 7th in there as well. When we find the pattern and establish it, then we can just say, hey, we're going to let this run out to infinity, and we're going to gather all the terms that we possibly could. So, cookbook-wise, what we need to do this problem is a list of the first several derivatives of 1 over x, enough to establish a pattern, and then a look at what this term might happen to look like for each of those things. So, this isn't too bad. If f of x is 1 over x, and remember that's just x to the minus 1, the derivatives of that are not bad, so I'm actually going to make a little chart. I'm going to make spots for the value of n, so the 0th derivative, meaning the function itself, the first derivative, second, third, fourth, and so on. What the nth derivative of the function looks like, so for the function itself is 1 over x. The first derivative by the power rule would be minus x to the minus 2, which is negative 1 over x squared. The second derivative, we can put that in exponent notation like that, in power notation, to remind us that we're still using the power rule. The second derivative would be negative 2x to the minus 3, or negative 2 over x cubed. The fourth derivative would be, now look what's happening here. We're going to bring a 3 down and multiply it by 2, and there's 2 minus signs. It'll be a plus. And I'm actually going to write this as 3 times 2, then x to the minus 4th. Again, I've done a power rule on this to get the next derivative down. And then after that, I'll bring a power rule. I'll bring this negative 4 down in front. negative 4 times 3 times 2 times x to the minus fifth. And I think we have enough to establish a pattern. So note what's happening. Positive, negative, positive, negative. These derivative functions are alternating terms, or alternating signs. The exponent, negative 2, negative 3, negative 4, negative 5, is going up by 1 every time. And the coefficient that's getting built is actually very recognizable as a factorial. And so for my third column here, I'm going to ask myself, what is the value of the function or some derivative of the function at our anchor point? Because remember, we're going to build this, and what I'm constructing are the values that are going to go into this numerator. Our anchor point for this problem is x equals 1. And I'm looking for the first, second, third, fourth, fifth derivatives evaluated at x equals 1. I need a bunch of them. So the original function at x equals 1, that's just 1. The first derivative evaluated at x equals 1, well, 1 to the negative 2 is still 1. How about that? The second derivative, negative 2 over x cubed, evaluated at x equals 1. So far, so good. The next derivative is 3 times 2 times x to the minus fourth, or 3 factorial, and then evaluated at 1, x to the fourth, or x to the negative fourth will just give us 1. And then the next one down, negative 4 times 3 times 2, that's a negative 4 factorial. And again, when we plug in a 1, the x to the minus fifth will just be 1. So to show you why this is good, I can come down here to n equals 5, and I can just tell you right away. 5 factorial would be the result, and then negative 6 factorial, then 7 factorial, etc., etc. Alrighty? So let's start building. Can I do this? Can this, is this going to fit in here? No, it's not. So I'm just going to show it to you one more time. We've got the values of this numerator here, and we're going to start loading up everything else. I'll rewrite it. And I'm putting in a reminder specifically that our anchor point for this problem is 1. Okay, first term. When n is 0, I'm up here. This numerator is 1, and I'm going to divide it by 0 factorial. And then times x minus 1 to the 0, because again, my first term corresponds to n equals 0, so 0 goes there, 0 goes there. And then I go to my n equals 1 term. Well, here, let's put in all that stuff first. Just knowing that n equals 1, I can build that much. And then what goes up here in the numerator? Another 1. And I'm running out of room, so I'm going to hit return, go to the next line. Here, plus. Now I'm at the n equals 2 term. Well, I can go ahead and build that much already just because I know I'm at n equals 2. The numerator, looking for this value for n equals 2, that is this one. For n equals 3, get that much, and then go up here. And look what's happening to the coefficients. The values that are coming out of my derivatives are canceling this n factorial that's built into the formula for our Taylor polynomial or series. Right now, if I covered this term, I've got the second order Taylor polynomial. With this, it's the third order Taylor polynomial, etc., etc. With the little bit of space I have left, I'm going to simplify these things. That's a 1, that's a 1, that's a 1. For this term, that's a 1, that's a 1. This is an x minus 1. For this one, 2 and 2 factorial are the same thing, so that minus is going to hang out and survive. Here, 3 factorial over 3 factorial, they cancel. and I have x minus 1 cubed. And again, this is good because now we've got the pattern. I don't need to go up here and start digging around. I know the extension of this, right? The next one's going to be minus x minus 1 to the 4th, and then plus x minus 1 to the 5th. And I can put on that magic dot, 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 which indicates this can continue as long as I want it to. The Taylor series is the full continuation of all the terms. But stopping at any one of these, I have a Taylor polynomial of order 2, of order 3, of order 4, of order 5, etc., etc. And if I were to plot this function on top of 1 over x, I would see some agreement. So maybe I should do that. Oh my goodness. Here is a good reason why actually trying to follow up and plot things is a good idea. Let's play Spot the Instructor's Mistake. Did you guys see what I did when I was building all these numbers? I made an oops with a minus sign. Fortunately, this can be fixed. Here's where the error crept in. Right there. I mean, that minus sign isn't an error, but the fact that I forgot to bring it over here and then forgot to put it here was a bad thing. But I found the error, so now I can fix it. How do I fix it? Well, I just have to go back and have a cascade of changing of signs, because the signs, SIGNs, of each of my derivative functions will now be the opposite. And so the signs of my numerical values are going to be the opposite. So let's see, that means this one's going to be a minus. That means this is going to be a plus. This one's going to be a minus. And so here, I'm just changing them all. And so on. Now, how did I recognize that mistake? Because I had intuition about what the heck I was building in the first place, right? I wasn't just cranking out numbers, plopping them on a page and saying, oh, that must be good. I was actually doing this. I went to Maple and I asked for a plot of my original function and a plot of what I had written down as the third order Taylor polynomial for that function. Right there, plot 1 over x, and then this business right here is what I had cranked out as the polynomial. Oh, go away, you. And the graph made no sense, because as I should expect, because I know what I'm doing here, right? We understand the principles we're working with. Here is 1 over x. The red curve is supposed to be my Taylor polynomial. Now, yeah, they intersect at x equals 1. That's great. But my Taylor polynomial is supposed to mimic the behavior of my function for some distance around x equals 1. Maybe a small distance, maybe a large distance, who knows? But that didn't happen. And so that made me go, oh my, I probably have a mistake. You see that, you do your work, you investigate whether it's reasonable, and then you can go back and fix mistakes. So now I'm going to see if this slightly better version of my Taylor polynomial is an improvement. And here I'm going to change the signs, just like I did before. So I got 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed. Let's see what this does. Oh, look at that. So now here's my graph. 1 over x again is this descending curve. And here's x equals 1. And look at how the red curve now nicely hugs and mimics the actual function 1 over x in a region that's centered on x equals 1. That's what we're after. And you know what? I bet if I went up here and added another term, I could get this agreement to go even farther. So like right here where the Taylor polynomial function is separating from the 1 over x curve, I bet with some extra terms I can make that better. So I'm going to go up here and continue the pattern. Now let's make it a 5th order. We know what the pattern is, so we can just keep adding numbers. Now, this problem was selected to make the coefficients easy to deal with. That may not always be the case. Okay, so I didn't make it that much better, but it didn't ruin anything. Or maybe the scaling is different, so it's harder to tell. But anyway, it's the same behavior. Blue curve is 1 over x. Here's the anchor point we chose, x equals 1. And our 5th order Taylor polynomial now is mimicking the behavior of 1 over x for a region that's centered on x equals 1, and that's what we were designing. And that is a Taylor polynomial, which by ... extends out to a Taylor series. Okay, bonus here. This at the top of the page is the corrected version of the Taylor polynomial, or Taylor series, for 1 over x, centered at x equals 1. This is the formula for Taylor series, generically, for some function and some anchor point. What people have a tendency to do is to take their function and try to construct this monster as is, like to go straight from whatever the function is in the anchor point and suddenly be able to discern all the stuff that goes in here without any intermediate work. That's a bad idea. Okay? What you really need to do is calculate the derivatives out one at a time, plug in the anchor point to all those derivative values one at a time, and assemble these terms one at a time, so that then, once you see the pattern, then we could write the full-blown Taylor series in its series notation. Ta-da! Every one of these terms is x minus 1 to a power, and let me label these. Remember, this was the term for n equals 0, n equals 1, n equals 2. And so, given that our Taylor series formula, in its tight series appearance, wants to start with a counter of n equals 0, this 1 needs to be n equals 0 term. This x minus 1 is the n equals 1 term. This x minus 1 squared is the n equals 2 term. So notice the distinguishing factor is just the exponent, and the exponent matches the counter at each term. For the n equals 2 term, the exponent is 2. For the n equals 3 term, the exponent is 3. For the n equals 1 term, the exponent is 1. For the n equals 0 term, do we say uh-oh? No, we don't, because x minus 1 to the 0 is 1. So it all fits. Okay? So when you're faced with doing a Taylor series problem, this is the Taylor series formula. Do not attempt to just dump stuff into this as it stands. Open it up, calculate the derivatives, calculate the terms, lay them out, and then use the pattern that you find to build the series notation.